Today, welcome everybody. So today we have Marta Spinelli from the Observatoire de Côte d'Azur in France. So she's going to talk about 21 centimeter cosmology and intensity mapping. So you can, so Marta, thanks for being here today, and you can start. Thanks.
Thank you so much. So I was promised to come to this seminar for a while, and sorry, last year was a bit a disaster. So what I'm going to talk about today is like 21 centimeter cosmology in like especially cosmic dawn and intensity mapping. A lot of you are familiar with 21 centimeter cosmology in general, but maybe some of these like cut about especially what are the problems, especially cosmic dawn, that are actually quite similar to the same one that we have for the post-reionization that people, for example, working in IRAX knows. So there are really common grounds. So the idea is really to present generally the problem and go a bit in more details in cosmic dawn and post-reionization. I mean, I think it's nice since there are a lot of students, just interrupt me when you want, and then if I say something that is not clear, I really like to explain stuff. So I just also want to say that a lot of this work has been started and continued with people working at the University of the Western Cape, where I was a postdoc now a long time ago almost. But so this is also a lot of this work is, especially the one on MeerKAT, is done in collaboration with the people there. And the PI of the experiment I'm going to discuss, the survey I'm going to discuss, this MeerKAT experiment is Mario Santos at the University of the Western Cape. Okay, so the talk is about hydrogen. This, you know, that hydrogen is a very important element for all the evolution of the universe. And this is just few phases where you can say that it's like super fundamental. You can recognize in this picture the cosmic microwave background here. And indeed, the release of the cosmic microwave background came from the combination of electron and proton in neutral hydrogen. So already since the beginning, the hydrogen played really an important role. Then there was this period of the dark ages that then the first star and galaxy started to shine. And so that's the period that is called cosmic dawn at very high redshift, where all this initial formation of galaxies and stars took place until the universe got completely reionized, and so all these neutral hydrogen, almost all these neutral hydrogen got destroyed by the presence of UV photons during the reionization. And the leftover hydrogen that we have these days is a good tracer of Lasky structure, as we're going to see, but it's not only that. It's also a very important ingredient for in the late evolution of the universe for galaxy formation, and galaxy evolution plays a really fundamental role in the way all these the galaxy form and the baryon cycle. So especially for cosmology, normally the two pillars that we have always been using for constraining the cosmological model are the CMB photons from the cosmic microwave background, as I was mentioning, since this is a very linear field and really amazing constraint for the cosmological parameter has been found, for example, by the experiment Planck that you see here in this little logo. And then regarding the late evolution of the universe, these, for example, surveys of the Lasky structure surveys where you go and count the galaxies has been super useful, or this Lasky structure study that we have now with the new theory technique. They have been proven to be as good as the CMB to constrain cosmological parameter. So we have two pillars for constraining our model. One is very early in the evolution of the universe, and one is somehow very late. And so I think that you all know that the huge power of 21 centimeter and why 21 centimeter cosmology is such an interesting subject is because with 21 centimeter, and in particular in the future, just to do a bit of promotion, the SKA Observatory, you can really use a 21 centimeter probe as something that completely goes from the beginning to the late evolution of the universe. It's something unique that cannot be done in a lot of ways, and so for cosmology is super important because you can finally cover this arch of cosmic time that you cannot cover with CMB, if not with secondary effect or Lasky structure, because you cannot push too far in counting galaxies. So you may all know already, and I reduce this, maybe you see better, I don't know if you see it or not. So the SKA is going to be composed by two locations and two main telescopes, a dish array in South Africa that you will know. Here you can recognize the MeerKAT dishes that are going to be part of a larger dish array, and these are the design in this rendering for the SKA dishes. And also a part that will cover lower frequencies in Western Australia, where there's a completely different shape of the way we're gonna, the antenna looks like. These dipole antennas organized in these big bunches of antennas together, and then a lot of these to construct a very beautiful picture of the universe. So what it's important for us in this frequency range and these different type of antennas that are around is that we can do, as we were saying before, with 21 centimeter, tracing the 21 centimeter line, all the epoch that are of interest in for cosmology, because we can, at this slightly higher frequency, we can do all the post-reionization universe, meaning that we can go to redshift 0 with SKO, we're gonna go up to redshift 3. And then from redshift 3 to redshift 6, where it's the start of the epoch of reionization, can be done with the high frequency end of the SKA low, and then we can cover going up to 50 megahertz all the epoch of reionization, a cosmic dawn, really going up for up to redshift 20, 30, depending on when they say 50, 30. But in any case, a very high redshift range. So what we have now, as I was saying, we already have these MeerKAT antennas, and part of this talk is going to be about how we can actually use one of these single dipoles here to understand something of the evolution of the universe. So the 21 centimeter signal, you may all know, but it's something that is computed with respect to a background. There are three fundamental temperatures that needs to be taken into account when we compute what is the actual this brightness temperature that we measure at our antennas. So there is a background temperature that normally is assumed to be the CMB. Then it's very important what is the temperature of the gas, intervening gas. And the third very important temperature is what is called the spin temperature. It is what sets the population of what is this actual 21 centimeter line in nitrogen. So this transition between this level and this level, and the way this level is kept populated is through this spin temperature. Now, in the way these three temperature evolves, give us how the temperature brightness that we can measure from Earth changes as a function of redshift, so as a function of frequency that we can change. And it's really what we were saying before, that we can really go from the dark ages to the post-reionization universe. So if we imagine to not looking at looking at the mean variation of temperature around the full sky, this is like how it looks like as a function of redshift. So as we were saying, the function of frequency. And so in the dark, and it's regulated by this equation here. So what you need to see here is during the dark ages, there's what is called collisional coupling, and collisional coupling keeps in this very dense, very early universe, the temperature of the gas and the spin temperature in contact, and this is like going faster than getting colder faster than the CMB. So in general, what you have is that this ratio is negative, and so you have a negative mean temperature for the temperature brightness. Then the universe expands. This collisional coupling is not so efficient anymore, so it's called collisional decoupling. And then the mean temperature approaches 0 until the stars start to shine again. So there are a lot of Lyman alpha, and so this Lyman alpha coupling push down again the temperature brightness, creating then when there are a lot of X-ray around this shape that looks like an absorption feature. That is what we are looking for at cosmic dawn. And then with all these X-ray presence, it gets hit more and more until it passes from absorption to emission. And so the part of the reionization starts. the spin temperature is not so important. It gets less important as a function of the evolution of the reionization. And what is actually very important to trace to reionization is this XH1 here. That is how the fluctuations of H1 changes. So what is the neutral fraction of hydrogen around the reionization until now, as we were saying, almost all neutral hydrogen got destructed and only the one that survives in dense cloud. So this means that at this late time in the universe, we can use H1 to trace the Lasky structure. So why this absorption feature that we were mentioning before is so important? So if you look again at the redshift when this is done, it's around redshift 20, we think, 2010. So this is a signal from the cosmic dawn. As we were saying, it's coming from the interplay between Lyman alpha and X-ray heating. And the nice thing is that the shape of this is not fixed, but we don't have a fixed theory for that, but we know that we can kind of change the shape of this absorption feature as a function of various cosmological parameters, for example, the minimal mass for halo that hosts H1, these type of things. And you can see this is just an example. There are various papers that study this behavior, but you can change the shape of this absorption feature as a function of this parameter. So if you can measure this absorption feature, you can actually pin down some important information about the cosmology at the cosmic dawn. Not only this is just the measurement of the global value of the temperature, but this measurement of the global value of the temperature give you hints on how you would like to, where do you think the fluctuation of the signal are. So it kind of drives, if we manage to measure this cosmic dawn signal before, for example, SKA law is completely in place, then you can drive the SKA law research in a particular area of redshift, and you would expect a certain value for the power spectrum and this is, for example, what has been used in LOFAR, the edges detection that has been claimed a few years ago now. I'm going to discuss this in a second, has been used by some LOFAR people to try to detect the same, but in power spectrum fluctuation instead of global signal. So the two kind of type of experiment talk to each other. So why instead the late time nitrogen distribution is so important? Because there's two super important information that you're getting there: the dark universe, but also the baryon, as I was saying. Cold gas in general, neutron energy plays a really key role in galaxy evolution at the late universe. And so if you want to really go back to the dark universe, you have also to understand the baryonic part. So there are, of course, here a lot of open questions that we need to answer from like dark universe part. What is, we still don't know what is the nature of dark matter, dark energy. What we can try to measure with this with hydrogen, if we understand then the baryonic part, is how this dark matter is distributed on the large scales, how this distribution, for example, evolve with cosmic time is a way to understand better dark energy, for example. And then at the other side, as I was saying, it's very important to understand the baryons. So what is the link between galaxy and dark matter halos? So how we can also do this with simulation, how these H1 galaxies are distributed in the cosmic web, and for example, what is the total cosmic H1 that evolved with redshift. This would be super interesting to see if, as you know, the radio telescope would see only the 21 centimeter emission. This is fortunately and unfortunately not the case, because you can not only see this 21 centimeter atomic transition, but also molecular transition and other atomic transitions from various celestial objects. Mainly you see a lot of synchrotron that is due to the electrons with relativistic velocity that do this spiraling in the presence of magnetic field and emits synchrotron radiation, but also free radiation, also known as Bremsstrahlung radiation, that is instead produced by the acceleration of electron when there is hot gas. And also in the radio sky, you are looking for a lot of other things, maybe things that we still didn't think about or still don't understand very well. So this is very beautiful, but what is the drawback of that is that when we look at the frequency for trying to look at the 21 centimeter line, what we see is actually, in particular for us, a lot of synchrotron emission. So this is why it's so important to disentangle the foreground and the signal, because if you want to do cosmology, we are measuring the radio band. This is what we are seeing, and behind this very bright synchrotron foreground, there's 21 centimeter signal that give us all this amazing information about the universe that we have discussed up to now. So of course, the idea would be, for example, let's try to avoid the very bright galaxy. This is our galaxy measured by the ASLAM. This is the ASLAM map, just rescaled at the frequency where we are interested in. And it's true that since it's the galaxy, we can try to avoid at least the galactic plane. But this foreground is quite complex. There's not only galactic, but there's also extragalactic foreground, point sources. So these are all things that pile up in front of this 21 centimeter signal that we are trying to measure. This is not the end of the story, because there's also the fact that we are measuring the sky with a telescope that has RFI, that has his electronic measuring things, the shape of dishes. So there is a lot of things that enters in the game, and so there is a lot of things that you have to take into account when you describe the noise. Also, for example, the scanning strategies and all this stuff. So the challenge of foreground is not only a problem of foreground and modeling the foreground, but it's also to understand how the foreground couples with the instrumental design and the way we take data. So how do we deal with foreground generally? There are various strategies. Here I just mentioned the three that are more a la mode. So you can either try to model the foreground, you can try to separate and clean, or you can try to avoid the foregrounds. These are the three main branch you can try to use. So what I'm gonna discuss today is how we use modeling for foreground for the cosmic dawn, and how we do separation cleaning for the post-reionization universe. And I'm gonna skip this avoidance technique that is mostly used for EOR. I can give you some hints. Maybe some of you knows already, but really the idea is that we use the foreground properties to kind of understand where we think that the foregrounds are not present, and it's only a clean EOR signal that we can use. So let's start from the cosmic dawn part. Please interrupt me when you want. So let's start with the cosmic dawn part. Of course, here I'm talking about a single dipole. This is the thing I'm mostly involved in. Hopefully, this cosmic dawn science is going to be done also with SKA law. So for a power spectrum point of view, maybe imaging. But here we are looking at this absorption feature that I was describing before. So what are we measuring for this dipole? So imagine one of these dipole antennas. Here in particular, I am in the northern hemisphere. And I have my single dipole antenna on the ground, and the sky moves on top of me. I have a single antenna, so the beam response of this antenna is huge. You can see it in this picture here. And so I'm measuring in the end, not really a map, but just one point at each frequency, because the beam is so large that I cannot trust exactly what I'm seeing. So I can just measure the final temperature of the antenna at every frequency. So since I know that synchrotron is kind of going up at lower frequency, what I expect are these power law that you see here as a function of frequency. So the frequency range, interestingly, for cosmic dawn is from 50 megahertz to 90 megahertz, 100 megahertz. It depends on the experiment. You can arrive up to 200 megahertz. So that is kind of the end of the reionization. So the start, sorry, of the reionization. So what are these different colors? For those who are not familiar, different LST. So at different time, when I'm taking my observation, I'm waiting for the sky to move above my head. So I'm gonna see different type of sky upon my head. So around LST 16, 17, I'm gonna more or less see the center of the galaxy on top of my head. So globally, the temperature that I measure on my antenna is higher than the one I measured, for example, at LST equal 5, where I'm here, and the sky is much colder in synchrotron. So when I take this measurement, I'm not only, of course, measuring the direct response of the sky, because I am seeing it through the beam. So the modeling of the beam is very important. It slightly changes the smoothness of this antenna curve that I'm showing you here. So how do we try to look for the absorption feature. So the absorption feature is somewhere there, is a dip in this very smooth foreground that I see. And the way we try to model it is that we know that this absorption feature is more or less Gaussian, or something that looks like more or less Gaussian. You can do much more sophisticated parameterization. You can use machine learning for that, but the base approach that has been used by the edges collaboration, I'm going to discuss this in a second, is really that, just modeling the full signal, the full measurement that I take in my antenna as something that is an absorption feature that has some Gaussian parameter to be fitted, and then this foreground plus the presence of the beam being modeled by like a smooth contribution that is what is called an n-term log polynomial. So it's something that is smooth and can have more or less term to be described. And the more term I add, the more the smoothness is actually something a bit more wiggly. So because the convolution between these very smooth spectra of the synchrotron emission plus the effect of the beam creates a more complexity. So I would need maybe more term in this log polynomial. So this triangular plot that you see here is actually done on data, on edges data. So on edges data, they measure this temperature as a function of frequency. They model it as a 5-term log polynomial plus an absorption feature with this flattening parameter, that is this tau here. And then they do an MCMC and they found their posterior distribution for the parameters. And you can see here that they can really measure that there is an absorption feature with a certain center frequency, a certain width, a certain flatness parameter. Now, as you can see here, what is the problem? This would be lovely. It would be exactly what we expected, but kind of fortunately or not, depending on how we interpret this, it is really out of the modeling that has been proposed before. So the modeling here, reasonable modeling are in gray, or for example, these dotted line here, but this is what the best fit parameter that the edges collaboration found. So this is really much higher than expected. And so this triggered, of course, a lot of debate. There are indeed, for example, a lot of other people, of course, that are trying to measure the same thing. So this is how edges look like. So it's not exactly the same dipole as I showed you before. It's a dipole that looked like this one. It's more like a table. And they did a lot of cross check. This is just their 2018 paper, but they published also a more recent paper where they really did some hard tests to try to understand what is could be wrong if nobody believes this result. But at the moment, they don't have another explanation than this is actual signal. At the same time, there have been a lot of experiments that tried. One succeeded to try to arrive at the signal to say something. This has been the SARAS-3 experiment that is actually floating on a lake. I'm going to discuss in a second why floating on a lake is not such a bad idea. It's a completely different type of dipole. These are all types of dipole that you can use. More or less, the idea is always the same. They have a certain response very big in the sky. You always measure this descending power law. So what they did, they tried to fit for the signal exactly as edges have seen it, putting a scaling parameter in front of this absorption feature as edges has seen it. And they find that the scaling parameter is compatible with 0, meaning that there's no need for this scale parameter. We also did some measurement. This is an experiment that is led by Lincoln in Harvard. A lot of years of work and optimization. There are a couple of papers describing the LIDA experiment. It's called Large Aperture Experiment to Detect the Dark Ages. I did only, of course, the last part of that analysis, so all the credit to the people that worked on the antenna. Details on the antenna are in this SKA paper in 2018. So we still have some data to finish analyzing. Savannah that is connected hopefully will work a little bit of the data, the latest data that we still need to analyze. So these data are taken with these triangular dipole antennas that you see here in the picture that are outriggers of the LWA in the Obro Valley. So what we did up to now with our data is we at least checked that we were seeing something reasonable, and we measured the spectral index of the synchrotron, like this foreground emission that we are seeing, and it's quite compatible with this black dashed and dot line are the modeling coming from different modeling for the foregrounds that we expect. And so, I mean, we are quite compatible with what is expected from the sky. So at least we are seeing something reasonable. We did try to find the absorption feature. We don't have at the moment the signal to noise. There's probably things that we could do better, and that's why we are always happy to have students to work on this, because there's a lot of data and a lot of maybe it's a question, or maybe not, in case just interrupt me. Okay, so this was the spectral index, but why this measurement is so complicated? Because to model, there's a lot of things that enter in the modeling of this instrument. For example, also the ground. Can I ask Magic to please mute? Because maybe it's, I mean, I'm okay, but maybe it's annoying for the people. It's okay. So there is a lot of things that enter in the modeling of the instrument. There is this ground plane that try to avoid the contact with the ground, but the ground is still very important. And we measured, Lincoln measured the properties of the ground on site, and we kind of tried to stress test the reconstruction of the absorption feature in this approach that I described up to now, as a function of how much we know actually the soil underneath the antenna. And if everything is like infinite and there's no effect of the soil, whatever, I have a perfect ground plane, everything is fine, and I can reconstruct whatever. Already, if I put a 3x3 ground plane, so there is something that is limited underneath my antenna, I start maybe getting things wrong if I don't correct for the effect of the beam, because the effect of the ground plane is actually entering in the effect of the beam. So you can do what is called chromaticity correction. A lot of people in the community does that. So chromaticity correction is just a way to introduce, again, a beam modeling inside the way we do the analysis, a kind of correct these spectra by the effect of the beam. So if you do that, it's much easier to get the exact result. What I'm going to show you here is that the problem is that, so if you know perfectly the beam, you can always correct for the effect of the beam. But if you don't know it properly, then this is a problem. And indeed, what we found is that if we change, for example, just a little bit the composition of the modeling of the composition of the soil, the permittivity, the conductivity of the soil, or if you change the way the soil is parameterized, we cannot reconstruct this absorption feature exactly as it is. So this is just to say that it's a very difficult measurement, but it's a measurement that kind of force you to understand perfectly your instrument, perfectly your environment, perfectly your RFI. So it's a very good stress test to understand what will be going on with, for example, the SKA law. So one thing I'm involved in, and for example, also Savannah, is this REACH experiment that is led by the Cambridge people. And one of the things they did, apart their own electronics, their own calibration pipeline, they also changed the data analysis pipeline. So they went for something that was this fit of the absorption feature plus a log polynomial to something more complex with more parameter that takes this chromaticity, so this effect of the beam, into account in a more consistent way. So if you're interested in this, you can read this nice paper from Dominic published a few years ago now that explain how the pipeline works. But basically you are kind of computing the effect of the beam in a Bayesian way on the fly, instead of knowing that the beam will kind of change your the way your spectra look like. Okay, so that's it for the first part. I still have 10 minutes where I'm going to discuss intensity mapping. I'm going to go fast on what is intensity mapping, because a lot of you people work in IRAX, so you know what is this about. But the idea is really that We can use hydrogen now that is left over in these knots of the cosmic web as a tracer, a biased tracer for matter clustering. In a way that is similar to galaxy survey. Indeed, you can also, at very low redshift, try to find each one galaxy one by one. But this is not feasible for cosmological purposes, at least not all of the cosmological purposes, because you need more volume, more large scales to actually constrain cosmology. So what you can do is do intensive mapping. So you kind of give up reconstructing the single galaxy and just collect all the 21 emission in these large pixel in the sky. And as you know, as we discussed up to now, since you have a one-to-one correspondence between redshift and frequency, you can actually have a tomographic view of the evolution of the universe. So this is good because it gives us a high spectral resolution. So with the high spectral resolution in a large frequency range, redshift range, we can understand things about dark energy and dark matter. So what we are doing with MeerKAT, we are using MeerKAT as a single dish instead of the interferometric full power of MeerKAT. Why we are obliged to do that? Because the distances between dishes is not short enough to actually resolve the large scale that we are interested in cosmology. So this is unfortunately a problem. That's why if you can construct your own experiment, of course, you put dishes very close to each other at regular spacing. In our case, this is not what we can do. But what we can do is to use each of these 13.5 meters dishes of MeerKAT as a single dish. And this is good enough to do at least large scale cosmology and to reconstruct also the BAO feature, maybe if not at all redshift. So these are data that we took in L-band that were superimposing the 11-hour field of Wiggle Z. I'll show you in a second why. And we have a particular technique to take data that results in these fringes, how the maps look like in the sky. So this is the first calibrated data. This is a lot of work done by Jingjing Wang and the pipeline she constructed started from CAT7. So what you see, what we have discussed up to now, when you finish calibrating your data, is the synchrotron emission. And here you can also see that these magenta dots correspond to the point sources, known point sources in the sky, and you can see that there are like brighter dots, spots that correspond to the point sources. So this is data in L-band. The PI is Mario Santos, and so this was really the first map, the first final map that we could calibrate with the data in 2019, the 2019 data. So okay, so here we have the synchrotron, but how we can deal with the synchrotron emission and to arrive to the 21 centimeter emission that we are interested in. We can do foreground separation or foreground cleaning with blind methods, for example. And so I'm gonna just very briefly show you a little result with a little example. So imagine we have this data cube, mock observation. This is done in simulation. I have 100 channel, a certain redshift, central redshift. I put inside the synchrotron, free point sources. I use a Gaussian beam that corresponds to the beam effect of my single dish MeerKAT experiment. I put very easy white noise. And then I do as the CMB people does. So I say that my data, it's actually a combination of foreground sources and a mixing matrix plus noise plus the cosmological signal I'm interested in. And the main question then becomes, so how many sources do I need to describe fully this cube? So what you can do is you construct what is called the frequency covariance matrix and take the eigenvalue, eigenvector of that. If you look at the eigenvalue, what you see is that in the first, for example, in our simulation case, it seems that in the first three, it's contain all the information and then it flattens out, meaning that these three directions are the most important one for PC, for the analysis of principal component analysis. So how does this direction reprojected on the data looks like, these sources? So the first one looks like that, the second one looks like that, and the third one looks like that. So if I go back on my simulation and look how the synchrotron, the free and the point sources map looks like, I see that these things are very, very similar. Maybe these two are a combination of these two. And so this is because the synchrotron is really, really dominant. So the first eigenvalue corresponds to kind of the direction where the synchrotron is stronger. Oh, sorry. So if I take then out from my data these 3 foreground sources, everything that is left is my signal plus my noise. So if I do that on my simulation, this is what my input 21 centimeter, how my input 21 centimeter signal look like, and this is how the PCR reconstructed signal looks like. So you see, I can do it. So it's possible on simulation to reconstruct using blind methods the presence of 21 centimeter pristine signal despite these very strong foregrounds. What about the reality? The reality is that if we go back on our 2019 data and take out 30 components, not only 3, because the more complexity there is in the data, the more components you have to take out. Still, I go down, I take out like most of the synchrotron emission maybe, but I still have contaminants in the data. You can even still recognize a little bit the presence of the point sources. So how do? We go back on the fact that we have at the moment superposing redshift with our data galaxy surveys. So we use WiggleZ. And when you cross-correlate WiggleZ and intensity mapping data that we collected with MeerKAT, you can kind of kill these residual systematics that you still see in the data. And indeed, in cross-correlation, we can obtain the detection of a power spectrum with a very high significance, 7.7 signal detection of this cross-correlation between the H1 and the galaxy. Because again, H1 and the galaxy, they trace the same elastic structure, just with different, in a different way, because we are with H1, we are tracing these baryons their cycle with star formation, while when you see galaxy, depending on how how is the setup of your galaxy survey, you see a different population, different bias of galaxies. So this is very good. It means that our data are not so bad. There's still some stuff that we have to understand about the data, but we have detection in cross-correlation. So to understand how we can kind of bridge the difference between what we see in easy simulation and what we see in data, a few years back now, we tried to set up this Brian Foreground Challenge, where we put together all the expertise that we have. I gave it to people to try their foreground cleaning technique. And at least we managed with more sophisticated, like at least beam modeling and noise modeling, etc., to challenge a little bit the foreground cleaning algorithm. And for example, we found this is not really a power spectrum, it's a line of sight power spectrum, and this is just to give you an idea of how much a real beam modeling can play a role. This has been already seen in some work that we did. The first author is now a lecturer at the University of the Western Cape, Siabonga Machahule. And the effect is that the wiggling that can be frequency, the way in frequency the beam change can cause very weird things that needs to be cleaned properly. So we managed to find a way to clean this a bit more properly, but this is a good example of how you should do this very difficult simulation to try to challenge this foreground clean technique. And this is just these spider plots that just give you an idea that different techniques behaves better or worse. So the more color, it's better. In some criteria of how you define how clean is the final map that you find, and some other in other techniques. So it's very good in general to mix different techniques to see different results, to try to understand what is going on. So just to say that, of course, there are a lot of instruments effect that we should try to put in this simulation to try to challenge this foreground cleaning technique, to try to learn also what is in the data, and then these instrumental effects, you actually learn it from the data. So for example, the fact that there is these side lobes in the beam, as I was mentioning before, but not only that these side lobes oscillates kind of in the MeerKAT beam as a function of frequency, the fact that your scanning strategy enters in the property of the noise, so noise is not white, but has to be modeled properly. And then also the fact that you have not at disposal all your channels because RFI is everywhere. So how we move forward? We can keep, of course, working on the data. We have a lot of new L-band data that are under analysis that are very good. We are also trying to finalize our UHF calibration. So UHF band in MeerKAT is slightly at higher redshift than the L band, so it's quite exciting because we can really push this 21 centimeter intensive mapping technique to slightly higher redshift. And of course, to understand of this, we need simulation. So what we are doing is a lot of work to try to mimic effect from the data and put it in the simulation. And then the final aim, of course, is to have this 21 centimeter auto-power spectrum detection. So without having to use a galaxy survey to kill the systematics, because we understand the systematics and we can clean the systematics. And so this means like a pure auto-power spectrum detection that is validated with simulation. And this is just, of course, something that we still did not achieve. And this is just an example of what we hope to achieve from simulation. So to conclude, 21 centimeter cosmology still have to prove its full potential. But I think it really offers an incredible window into how we can study the universe. And I give you two examples of cosmic dawn and post-reionization. In cosmic dawn, I really think that the global signal experiment are a test ground to understand like the nitty-gritty details that could be helpful for the SKA, but in general for a lot of other experiments. And there are more experiments in global signal to come that they can really, with improved technology, improved data analysis pipeline that can really be important in dealing with all these effects that I discussed, like the soil and everything. Regarding the post-reionization, intensive mapping surveys are taking data. Some will start soon. I know that IRAX is under construction, so this is all very exciting. Detection at the moment exists either in stacking on or in cross correlation. So we still have to prove that we can do better than galaxy survey, but I think we are on the right path. We are analyzing data, especially for MeerKAT, and there's a lot of effort in understanding really the way we are taking data, because it's very new. If we can do something different, how we can adapt this to the SKA. And of course, we need to keep improving simulation for the signal, for the foregrounds, but also for the instrumental effect. And I think that really all these will prepare us for the SKA era. And hopefully when everything is going to be understood and everything is going to be set up for the SKA, we're going to really understand things about cosmic history using 21 centimeter. And with this, I finish. Thank you so much.
Okay, thanks again, Marta, for the talk. Very interesting about the intensity mapping part. So we can take questions from the participants, maybe. So we got a lot of people that joined. Yes, Gingy.
Hello, hi Marta. Yeah, how are you doing?
Ciao, Indy, ciao.
Ciao. Yeah, so very interesting. I wonder for the cosmic dawn experiment, apart from REACH, the MIST is some new instrument. This MIST.
So MIST, I think, yeah. So it's I think it's a very cool concept that mostly Raul Monsalve and collaborators are developing. So the idea that they have is that the setup of the experiment is quite similar to EDGES, but then what they're trying to do is to characterize the soil and to change soil location without using a ground plane. So because we know, as I was showing in this test that we did for LIDA, that the presence, the modeling of the soil and the presence of the ground plane kind of complicates a lot the shape of the signal. So the signal gets more, instead of being very smooth, it gets this wiggling coming from the beam response. So what they are trying to do is to bring this dipole in different soil location with like an expert in like geology that knows how to model the soil and try to understand if they can do this without a ground plane, but only understanding well the soil. So they have very nice results. They still didn't do any cosmological analysis, but I think it's a very cool concept, and they have very nice data. They have explored already a couple of locations, but I think they're going to explore more. And I think it's a nice idea that you can move an experiment, so you can kind of take with you all the systematics related to exactly the antenna, and try to see if you actually see the right thing you expect.
Yeah, just a question. So do you mean they carry the same edges is everywhere in the world.
It's not really edges, it's something, but it's very similar. Yes, it's a dipole, one of these table-like dipole. So,
okay.
Yeah. Thank you for the question.
Okay, more questions? Okay, otherwise I have a one question by Tony.
Hi, hey Marta, thanks for the cool talk. I think you said something in the beginning, maybe you alluded to how the cosmic dawn absorption signature looks in the power spectrum space. Did you say something about that?
Yes, so I said, yeah, so it was to motivate, well, I think I saw it, I mean, I don't have a plot, but I had a plot. So the point is that depending on how the absorption feature looks like, you have theories that gives you the relation of how then the power spectrum should look like. And one obvious thing is that the more it's deep, the higher the power spectrum should be. And so if you measure an absorption feature, you can try to then go to interferometer and say, okay, I expect my signal to be here. Do I see it? So it's kind of a very informed research at this point. It's not more blind search for these. Of course, you have to believe that you actually can measure the absorption feature with global signal. I know that some people don't believe that, but if you do, then you can look for the signal at power spectrum level. And this is what this Gelot et al. Paper did. They tried with LOFA to arrive at the same level that was predicted by the very deep absorption feature measured by edges. And they are still not there. So they could not still disprove edges with the power spectrum limits.
Very interesting. Okay. So this is absorption features are like a monopole.
It's a monopole effect, yeah.
So you would see this at like low K-perp, or is it like K-perp is 0 or something? Does that make sense?
So you can, yeah, so you need to look for other features, right? You need to look at how this translates into a power spectrum, because in otherwise in interferometric mode you cannot see the monopole as it is. So it's kind of very it's a very different measurement of the same thing. So you cannot see it's like you cannot measure the absolute value with interferometry, but you can do it with one of these single dipole experiment. So for example, the measurement that LWA has, the zero offset is taken from LIDA. So using this outrigger in the LWA results.
So this thing will just affecting the total amplitude of the
just the total amplitude. Yes, exactly. But then my point was that if you have a theory that matches the shape, this theory also predicts the power spectrum, because this theory predicts the shape of like the distribution of matter, right? Because these are simulation that includes, so you can compute the global signal with simulation that starts from halos. So you start from like a halo distribution, and then you compute the global signal. So if you manage to have the right combination of astro and cosmological parameter that gives you the right absorption feature, you have information on the power spectrum too.
Yeah, sure. But this what the red block showing is something really of high redshift. Like so this
is where you're gonna be there, right? It's something between 50 and 200 megahertz, more or less. So we're gonna go there with the SKA law.
Oh, so this is the major absorption trough, not the. There's two absorption trough, right? There's a major.
So there is. So here I don't. I mean, I kind of. This one is also an absorption trough, but this one here, you cannot measure it on the ground. You have to go on the moon. This is why there is this experiment on the moon because you are blocked by the atmosphere. You cannot arrive. You cannot go below 20 megahertz. Actually, I mean, that's why everybody stops at 30, 40, because it's really, really hard to go lower than that. And then you cannot go anymore. You don't have signal.
Okay.
But yes, also
Okay.
this one is an absorption feature. Yes.
Okay, more questions or comments? Otherwise, we can say thanks again to Marta, and
The pleasure.
we can
Thank you.
see you in the next seminar that I will send the email about it. And yes, thank you very much, everybody, for coming, and see you next time. Thanks, bye.
Thank you. Bye, everybody. Thank you.